Hello everyone. In last lecture we have discussed what is semi-empirical mass formula, and also we have derived expression for volume energy correction and for surface energy correction. In today's video I am going to discuss about Coulomb energy, asymmetric energy and pairing energy. Okay, now let us see the first one, Coulomb energy. Okay, we all know that. Let us suppose if you consider a nucleus, and this nucleus consists of protons and neutrons. And each proton is having positive charge. And we also know that from electrostatics, if there are two positive charges, then they repel each other. And also in nucleus, each proton is going to interact with all the protons which are present in the nucleus. Here, because of its positive charge, Coulomb repulsive force are produced due to the mutual repulsion between protons which are positive, which are positively charged. This also reduces the binding energy of the nucleus. And let us calculate this Coulomb energy. Here what we are going to do to write Coulomb energy correction, first we are going to consider a charged sphere. That is, we are going to consider a sphere which is uniformly charged. And here from electrostatics we have one equation, that is self energy of uniformly charged sphere, which is given by E is equals to 1 by 4 pi epsilon naught into 3 by 5 q square by r. Here q is the total charge of the sphere and r is the radius of the sphere. And here charge is uniformly distributed throughout the sphere. This is the self energy of the uniformly charged sphere. We are going to use this equation, that is nucleus is having protons and these protons are uniformly distributed in the nucleus and these protons are having positive charge. So we are going to apply this equation to the nucleus, that is self energy of the nucleus is given by E is equals to 1 by 4 pi epsilon naught into 3 by 5. Here q is the charge and proton is having plus Ze as its charge, and in place of q we are going to substitute Ze, that is it becomes Ze square divided by, we know that radius of the nucleus is given by r is equals to r naught a to the power 1 by 3, where r naught is the constant and a is the mass number. If you substitute this value in the equation, we are going to get r naught a to the power 1 by 3. But here we are going to replace, if you solve this, if you simplify this equation, we are going to get it as a z square and e square. But in this equation we are going to replace z square by z into z minus 1. Here we are going to replace z square by z into z minus 1, because there are at least 2 photons are required for Coulomb repulsion. That's why we are going to replace z square by z into z minus 1. If you replace z square by z into z minus 1, then we are going to get E is equals to 1 by 4 pi epsilon naught into 3 by 5 into E square z into z minus 1 divided by r naught a to the power 1 by 3. Here 1 by 4 pi epsilon naught 3 by 5 E square divided by r naught is constant, so I am going to take it as a small a c, which is the constant value, and I am going to write z into z minus 1 divided by a to the power 1 by 3. This is the Coulomb energy correction. Okay, now let us see the next one, asymmetric energy correction. As we have already discussed Coulomb energy correction, and Coulomb energy correction seems to indicate that it would be favorable to have less protons in nucleus and more neutrons, but it is not true, because the nucleus, which consists of a equal number of neutrons and protons, are more stable as compared to the when the number of neutrons not equals to the number of protons. And one more thing, the nucleus which consists of a equal number of neutrons and equal number of protons are called symmetric effect, and the nucleus which consists of a more number of neutrons as compared to photon, or more number of photons as compared to neutron, are asymmetric effect. And one more thing, asymmetric energy correction is the quantum effect arising from the Pauli's exclusion principle, which only allows 2 protons and 2 neutrons in each energy state. And also asymmetric energy, it is going to decrease the binding energy. Okay, now let us discuss asymmetric energy correction equation. Here I am going to consider a nucleus. Here I am going to consider in atom, electrons revolve with the different energy levels. In the same way, neutrons and protons are going to occupy in different energy levels in the nucleus. Here I am going to take mass number 12. This nucleus consists of number of neutrons 6 and number of protons 6. And these 6 protons and 6 neutrons are occupied in different energy levels. It is neutron, 2 neutrons, 2 neutrons, 2 protons, 2 protons, 2 protons. And the energy difference between two levels is E. And also I am going to consider another nucleus which consists of different energy levels, and its mass number is 12, same, but neutron number is 10 and proton number is 2, and these 2 protons occupy first energy level, and these 10 neutrons are going to occupy different energy levels. And even though these 2 nucleus are having same mass number, but their nucleon number is different, and the energy of the system is also different. Let us suppose here in this equation we can see that there are, as compared to this system, there are excess of 8 neutrons. Let us write it. There are excess neutrons, and these excess neutrons are is equals to 8, or we can write it as a n minus z, where n is the number of neutrons and z is the number of protons. It is 10 and it is 2, and this equation gives 8. So excess neutrons in this nucleus is 8, or n minus z. And one more thing, that is, if you want to convert this nucleus into this, here we need to convert 4 protons into neutrons, that is these 2 neutrons and these 2 neutrons. We need to convert these 4 photons into neutron. These 2 photons convert into neutron and occupy this level, and these 2 photons convert into neutron and occupy the next level. And when photon is converted into neutron, 4 neutrons are having excess energy as compared to the previous photon version. That is, here let us discuss it. Let us suppose here, if you want to achieve this nucleus, we need to convert 4 photons, that is, convert excess photon into neutron. That is, here using this equation we can write, we need to convert 4 photons into neutrons. So we can write from this equation n minus z divided by 2. This is the excess neutrons which are required to create in this nucleus. And when we convert this nucleus, that is, there are 2 photons and already existing photons are 6, the converted photons, these 2 and these 2, total 4 photons are converted. And here you can see that these 4 photons are having excess energy. Here these photons jump to this level and it is having energy difference E. For each photon the energy is E, and for next photon energy is E. Then these photons jump into this level, and here we can see energy difference E plus E plus E, totally 3E for one photon and 3E for second photon, and totally here we can see that 8E is the total energy of the 4 photons which are converted into neutrons. These neutrons are having excess 8E energy, that is energy of 4 neutrons is equals to 8E, or we can write it as a 1 by 2 4 into 4 into E. And here we know that 4 is nothing but n minus z by 2. So if you substitute in this equation, we are going to get this equation 1 by 2 n minus z by 2 n minus z by 2 into E. Or we can write here one more thing, n is equals to a minus z. If we substitute a minus z here, we are going to get a minus 2z. So totally 1 by 8 n minus a minus 2z whole square into E. E, there is a relation between energy and mass number, and which is energy is inversely proportional to A. And if you substitute this value, then we are going to get the excess energy of 4 neutrons is equals to A minus 2z whole square divided by A. This is the excess energy of the 4 neutrons. Okay, now let us calculate the energy difference between two systems. The energy difference between two configurations, which is equals to E A, that is asymmetric energy, which is equals to A minus 2Z whole square divided by A. This is the energy difference between two configuration or asymmetric energy, that is here 8. Here 1 by 8 is the constant, and we are going to represent it by small a subscript capital A. That is, we can write energy correction as a A subscript capital A minus 2Z whole square divided by A, and asymmetric energy is going to decrease the total binding energy, so we are going to denote here negative sign. This is the asymmetric energy correction. Let us discuss pairing energy correction. Pairing energy correction, and this is the pure experimentally observed phenomena, and here I will try to explain by taking some examples. That is, I am going to consider a nucleus with different energy levels. Here I am going to consider mass number as a 8 and number of neutrons 4, number of protons is equals to 4, and these protons and neutrons occupy energy level. And one more thing, here I am going to take mass number 9 and number of neutrons is equals to 6 and number of protons is equals to 3, and this is how protons and neutrons occupy energy levels. And in this example I am going to take same mass number 9, but number of neutrons is equals to 3 and number of protons is equals to 6. Here this is how. And in this case I am going to take mass number 10 and number of neutron is equals to 5, number of protons is equals to 5. Here we can see that the number of neutrons and number of protons are same, that is, it is even. Here number of neutrons are even, the number of protons are odd, that is, this is the system of even odd, and here odd even, and here odd odd. And the pairing energy correction is given by AP divided by a to the power 3 by 4, but here we are going to write plus. For even nucleons we are going to add pairing energy correction, and for odd configuration we are going to subtract pairing energy. And one more thing, for even odd or odd even configuration we are going to do nothing, that is, we are multiplying pairing energy by 0. Okay, this is all about pairing energy. Here plus is for even nucleons, minus is for odd and 0 is for even odd even nucleons. So far we have written volume, surface, coulomb, asymmetry, pairing, energy corrections. Now we need to substitute all these energy values in a binding energy equation. If we substitute all the values, then we are going to get the final equation. B is equals to AB into A minus AS, A to the power 2 by 3 minus AC Z bracket Z minus 1 divided by A to the power 1 minus 3 minus A minus 2Z whole square divided by A plus or minus AP divided by A to the power 3 by 4. This is the final equation, and we call this equation as a semi-empirical mass formula. Here we are going to add volume, energy correction, and we are going to subtract surface, coulomb and asymmetric energy. Then we are going to add or subtract for pairing energy. Okay, this is all about semi-empirical mass formula.